I can hear you.
Awesome. Sorry, the Zoom meeting I think got confused. The ID got confused in the invite. So sorry about that.
Yeah, I ended up in a collaboration meeting with Pamela Gay and her colleagues.
So were you like, "Hi guys"?
I just sat there quietly for a bit and they didn't say anything, so I left.
I'm so sorry. The
It's
meeting ID
okay.
I think it was something that I had from previous things with Dr. Pamela that we because we do a weekly hangout all the time.
Right, right.
She's a regular on here. So let me so I saw that at the very end. I had no idea that it was actually copying and pasting that one. Let's see. There you are. Everybody can see you now.
Oh, hello everybody.
Can everybody hear her okay? I might need to turn it up. We can hear her. How is her volume? This is Dr. Katie Mack, guys. Just made my dog go nuts. I'm sorry. And do you want to? So while we're sound testing, do
Yeah.
you want to? Can you read the chat, or are you able to see it?
Uh yeah, I can see the chat. Yeah, I'm trying to figure out this is my first time on Twitch, so I don't know how any of this works, but I can see the chat. So
Yeah.
I can't see you in the Zoom meeting. I can
Right, because
yeah.
my video is being taken up by Twitch.
Okay. Yeah.
Yeah. So you hear me. What you're
Yes.
hearing me is real time on my stream. It's going to be delayed. That's why I always say just mute me.
Okay, cool.
Yeah, but the chat. Yeah, if you guys don't know who Dr. Katie Mack is, she's an astrophysicist and she's absolutely amazing. And I even said it that her Twitter is worth following. It is. She's that's the one thing I absolutely adore is that you're able to say things in a very in a Twitter message, even when we had fewer characters. But
Yeah,
do you?
this new 280 thing is totally changing everything. I don't I have just there's just way too much room.
Even people are saying that. Yeah, one of my favorite Twitter feeds. Yes. And so what? I know this because I remember it myself. But
Mhm.
what were some of your most famous tweets? Because that's really. I know this sounds crazy, but
So yeah, so I did one about eclipses that got really famous. So every time there's an eclipse now, this tweet I did about eclipses shows up, and it's just like eclipses as emojis. Like so, there's a sun emoji and a moon emoji and an earth emoji, and so depending on how you arrange them, you can demonstrate the different eclipses. And so I did that, and I did one with like the sun and the moon and the earth, and that was the solar eclipse, and then the moon and the sun and the earth and the moon, and that's a lunar eclipse. And then if it's the sun and the earth and the moon, sorry, the sun and the moon and the sun and the earth, that's apocalypse.
yeah,
So
that's what. Yeah, so solar eclipse, lunar
yeah,
eclipse, apocalypse.
yeah,
Fraser
it
just
works
said
much
that.
better as a tweet than
I know,
explaining
I
it
know.
in
Well,
words.
I totally understand. But yeah, you had that one, and then the LIGO announcement
um,
when we
yeah, I
detected the
don't.
first gravitational wave.
Yeah, I don't remember what I said about that.
That was a good
Oh,
one.
there was a thing with like doing the gravitational wave chirp sound.
Yeah, the chirp.
Yeah, yeah. So the sound that it makes, if you translate the waves in space-time into sound, then you get a special kind of sound for when black holes collide or when neutron stars collide. So you can make that noise, and it sounds like ooh.
Yeah,
So
exactly.
I got a whole bunch of physicists to record videos of themselves doing that little whoop sound, and it got onto like the New York Times, and it was really fun and silly. But yeah, I think that the tweet I'm most known for is where I was just sort of snarkily replying to a climate change denier, and somehow like J.K. Rowling picked up on it and retweeted it, and it ended up being this like huge thing, and then before I knew it, like my following doubled, and there were like I was in the newspaper, and it was just bizarre.
Yeah, yeah. And so, what was that tweet? What did that entail? Because I deal with a lot of that too, obviously, as you can
Yeah,
imagine.
yeah, I can imagine. Yeah, so I was tweeting about how climate change makes me sad, and how we're going to lose all these great things. And this guy tweeted, that climate change is a scam and I should go learn some science. And I said something like, well, I don't know, man, I've already went and got a PhD in astrophysics. Like, more than that seems like overkill. And I was just like replying to him. I wasn't trying to make a big thing, I was just saying like, I did learn some science. But somehow people started retweeting that, and then it just completely blew up, and my phone was just going crazy, and then I was getting messages from people I hadn't heard from in like 20 years. It was bizarre.
Yeah, so Joe's actually linking the tweet. Nice job, Joe.
Yeah.
And someone was like, that was you? I love that tweet.
Yeah.
I've seen that. Now everybody knows. Exposed. So,
yeah.
But you have a book that's upcoming, like, a few years, but that's happening.
Yeah, I'm writing a book. It's so much fun. I never really thought about writing a book before, but recently it seemed like it might be a fun thing to do. So I decided to write a book about the end of the universe. And so I'm like 2 chapters in now in terms of drafting the book, and I'm part of chapter 3, so I'm getting there. So it's been picked up by Scribner, and it will be published in 2020. So the basic idea of the book is to talk about all the different ways the universe might end and what those would look like, and how we're finding this out, and like what the future observations will tell us. So it's surprisingly fun.
Yeah.
I didn't know that writing about the ultimate destruction of all things would be so joyous.
Yeah.
Like, there's probably something wrong with me that I really like this sort of stuff. But I was writing one of the chapters, and I had this whole thing about the Andromeda galaxy colliding with the Milky Way, and how it's going to be this huge thing, and then and later on, around the same time, the sun's going to like expand and boil off all the oceans and destroy life on Earth. And I was like, yeah, this is really cool. So
Fraser just says writing a book is a fun thing to do. Nobody who's ever written a book said nobody who's ever written a book.
Yeah, I mean, I'm still at the sort of stage where this is kind of a fun hobby that I'm doing, and I'm getting to write about the fun things, and I haven't started any of the editing yet. So yeah. I'm sure that it gets more difficult and more arduous, but at the moment I'm just kind of playing around with like destroying things. So
yeah,
that's fun.
And then people, I know people even here on Twitch, that will be one of the things that already, I'm sure people are already interested, because I get asked about the big crunch. The big freeze.
Yep.
So I'm guessing you'll probably be covering things like that. If anybody doesn't know, do you want to describe what the big crunch would be?
Yeah. So I can go through all 5 of the scenarios.
I would love that. I would love that. Okay. Yes, please.
Okay, so Big Crunch is, so the book starts out with like some introduction, like what's happened till now, whatever. But then there's the Big Crunch, and the Big Crunch the Big Crunch is kind of an old idea, and it's probably not going to happen. But we don't know for sure. So the way the Big Crunch works, like right now, the universe is expanding. The way it's expanding is that everything's getting farther apart from everything else. The things themselves are not getting bigger. So like we're not getting larger, the galaxy is not getting larger, but the spaces between distant galaxies, that's getting larger. And that's been going on for a long time. And like it started off from the Big Bang. And depending on what happens with the expansion from here on out, that in principle, that expansion could reverse. And so if that happens, if the expansion that's happening now turns around and things start getting closer together again, then what happens is that, galaxies start to collide with each other really often. And then the universe sort of fills with this radiation from like the radiation that's left over from the Big Bang is still wandering around in the universe. We see it as a sort of microwave background, but that radiation would start to get compressed. So everything would get hotter, and then the light from all the stars and galaxies would start getting compressed. And so space itself would start to like get extremely hot and dense with radiation. And then the stars would ignite, like the surfaces of the stars would ignite and everything would blow up. So that would be really interesting. So, and then, ultimate destruction, basically. So that's the big crunch. And so I do the big crunch first, and then there's the heat death, which is also known as the big freeze, which is where the universe currently expanding is expanding faster and faster, which is happening, and that seems to be the most likely thing. It'll just keep expanding faster and faster, and so galaxies get farther and farther apart from each other, and eventually we get to a situation where we can't really see the other galaxies anymore, and everything kind of fades away, and then all the stars die, and then the particles decay, and you have this sort of big, empty, dark, cold universe that kind of exists forever in this sort of completely useless state of a very low level of radiation. So that's the heat death. And then the next one is the big rip, which is like the heat death but worse. So this is where you have the universe is expanding faster and faster, and dark energy is doing this. And then dark energy kind of goes wrong and starts not just pulling galaxies apart from each other, but ripping apart galaxies themselves, and then tearing apart solar systems, and then planets, and then like atoms and stuff like that. And eventually the entire universe is just torn asunder. And at some time in the future, this would happen. And I think at the moment, the big rip is not ruled out. Like, we don't have any particularly good reason to believe that can't happen. And in fact, it's not. It's like, based on some of the data, it's actually more favored than a regular heat death. But the time scale would be huge. Like, I think the last time I estimated it, it was like something like 100 trillion years is the soonest it could possibly happen. So
we won't be here.
yeah. I mean, it's long after anything important.
No need to RSVP, guys.
Yeah. But it's still kind of a neat idea. And then, so there's the big rip. Oh, and then vacuum decay. That's my favorite one, actually. So vacuum decay is where basically you have like this bubble of quantum death that it starts at one point in the universe and then expands through the rest of the universe and destroys everything. So that's a fun one, and that's totally possible based on our current measurements, but unlikely. Certainly unlikely anytime soon, but like, unlikely doesn't mean it can't happen. And then there's a final one, which is where you have sort of parallel universes that collide with each other to make a new Big Bang, and then they sort of separate, and then they collide again. And so you have this kind of clapping of universes that through like an extra dimension, and that's a sort of more speculative one, but that's also possible.
And is that all 5? Did we go through 5?
Yeah, that was all 5.
Oh man, because they're all so. Well, I guess the heat death versus the big rip. So yeah, you're right. Those I think a lot of people in here would read books about that. Absolutely.
I hope so. Yeah. I mean, I don't know. I find this stuff super, super fun. I hope that other people do too.
Yeah, no, and people I think are I don't know why, but people, it's funny when talking about space. I think it is a reminder of your own mortality.
Yeah.
But
yeah, sorry, go on.
No, I was just gonna say, like, with these time scales, this is space, the universe. And we're not even, I don't even want to bring up the whole idea. I can't even say it. Maybe you can, of the cosmic calendar, Carl Sagan's cosmic calendar. Like, we only have been here in terms of, I think, like the last second or something.
Yeah, something like that.
That's good to know. Yeah, I'm totally paraphrasing that, by the way. Someone asked, what's the rate of the expansion? Do we know how much it's accelerating? I can only say faster than the speed of light, but do you know the rate?
Yeah, so the rate of expansion is, so it depends on how far apart things are, how quickly they're expanding. So it's like, if you have a uniformly expanding space, then nearby things, over a small amount of time get a little bit farther apart, and more distant things over a small amount of time get farther apart. So like, if like nearby things,
I have a rubber band. I have a rubber band with these, and I even made the tick marks not to have, and it's probably hard to see, but I didn't make them all similar for that reason.
Okay.
So
Yeah.
to kind of dim, it's a very thin rubber band. I have a better one at home, but is that kind of what
Yeah.
you're saying there?
Yeah. Yeah. So like the two marks that are really close together are expanding apart slowly, and the two parts marks that are far apart are expanding apart really quickly. So there is a distance where the expansion speed between 2 points is faster than light, but for the for nearby ones, it's not. So the way that we measure the expansion is we measure it in kilometers per second per megaparsec. So a megaparsec is a million parsecs, and a parsec is something like 3 light years.
Mm-hmm.
So it's 70. So if you have something that's 1 megaparsec away, it's moving away at 70 kilometers per second. And so it kind of scales. So farther away things are going faster, and nearby things are going more slowly. But that rate is increasing over time, not in a way that we can measure the increase at like from day to day, or even year to year, but we can measure the increase based on what the expansion rate was in earlier times. And like at very early times, the expansion was faster, and then it started slowing down, and then it just started speeding up again about 5 billion years ago. So it'll be faster in the future. But yeah, there is a distance where the expansion speed is like faster than light, and that's okay because space is getting bigger. Nothing's traveling through space faster than light. See what I mean?
Right.
Yeah.
And that's one thing I was trying to describe to people is, how tricky it is to talk about how photons move in an expanding universe.
Yeah.
That's really difficult for me to maybe, I don't know if you want to try to, I know you kind of already broke that down a bit, but like saying that something left, a certain point during, let's say we can see a galaxy, 12 billion light years away, or something like that, and how that traveled through space and what we're seeing now. You have to account for space expanding.
Yeah, so it's really interesting. I mean, the expansion of the universe makes everything super complicated in cosmology in terms of like figuring out what you like. Even just saying like now, like the concept of now is really complicated in cosmology because everything you look at, you're looking at it in the past. So every time you look at a distant galaxy, you're seeing what it was doing, millions or billions of years ago. And so you can see, like, you can watch a supernova happen, like a star explode in another galaxy. But you know that it was, that actually happened millions of years ago, but you're watching it now. And millions of years ago, you wouldn't have been able, like, the information couldn't get to you. So it's this kind of bizarre thing. So when we see something happen in the universe, we have to kind of take into account that the light travel time means that we're seeing it at a different time than when it actually happened. And we're also like watching the past happen as we go. I'm not sure. I lost track of the question.
I know. It is so complicated. And this is what I try to do live, and I'm like, then I just end up, moving on to another question because that one's, unless you have, a thing to draw and then, that would be useful, but not right now. I'm saying like, unless I had something to kind of show that, but even then, like, I wouldn't want to mess that up because it's such a cool thing too. And it took me years to understand, listening to so many different things about it to really lock in that.
So here's a really cool thing about it. There are things that we can see now, like there are galaxies we can see that are so far away that they are currently moving faster than the speed of light away from us in terms of the relative distances and the change with time. And so, but we can see them because we can see the light that they let off before they got that far away. So we can see them as they were a lot earlier than now when they were moving more slowly away. And so there are things that we can see now that we will never be able to see, like the future of that galaxy. Like we can see part of its past because the light has left that galaxy, but now it's so far away that it's way beyond our horizon. So our horizon is the distance where things are so far away that the light doesn't have time to reach us, like it can never get to us. So the horizon is defined by the distance where if light left that point at the Big Bang, at the moment of the Big Bang, it would only just be getting to us now. So anything farther away than that has not had time for the light to get to us since the Big Bang. Okay?
Right, because that time doesn't exist right now.
Yeah, because there was nothing there, right? I mean, that didn't exist. So
right.
So there's a distance that's our horizon, and but the horizon isn't a constant thing. So there are things that were within our horizon that are now outside our horizon because of the way the universe is expanding. And also, you would think, okay, so when I say that the time that we have, that the horizon is defined by, how long it takes stuff to get to us since the Big Bang, you would think the horizon would be 13.8 billion light years, because a light year is how far light can travel in a year. It's been 13.8 billion years since the beginning of the universe. But actually, the things that we see far away we can see things up to like 46 billion light years away, because they were within that space, but then the space got bigger. So where they are now is 46 billion light years away, but they weren't that far away when the light left them.
Right.
So we can see that a much larger volume of the universe, in a sense, because the universe has gotten bigger since we looked at it.
Right. And that makes sense to me. Like describing that is extremely difficult, I've found.
Yeah.
And then again, not wanting to botch those numbers just because they're so cool, and trying to explain that, something that already kind of turns my brain into mush to some other people, it gets really difficult. But there is a question that I did see that I know you can talk about, because I've heard you describe it in things that I've watched of yours years ago. What's the difference between dark energy and dark matter?
Yeah. That's an interesting one. Like, I think the naming of dark matter and dark energy are a little bit unfortunate because, first of all, neither one is dark in the sense that, like, neither one is black. Like, it's not a dark color. They're invisible. They're both invisible. And they're probably not related to each other. We call them dark because we can't see them and we don't know what they are. And that's common to both of them, but they don't seem like they act in basically opposite ways. So dark matter is some kind of matter. So the matter is like something that has mass, right?
Right.
So, the earth, people, all of those things are matter. But it's some kind of matter that seems to be completely invisible. So it doesn't interact with light. It's not, it doesn't reflect light. It doesn't emit light. It doesn't absorb light. So we can only see that it's there based on how its gravity affects other things. So we see that the gravity, like the motion of stars and galaxies, appears to suggest there's more gravity in the galaxy than we thought there was. And dark matter is something that could account for that. So we see lots of evidence for dark matter out there through things like how things move around, and also through things like how light is bent through the space that's bent by dark matter being massive. So all of that gives us evidence that dark matter is there. So it's just some kind of matter that we can't see, basically. It has gravity. It acts like it's some kind of particle that, for whatever reason, just doesn't interact with light and electromagnetism. Whereas dark energy seems to be some property of the universe that, like, makes the universe expand faster. So we don't know exactly what it is. It might be a cosmological constant, which is just like a property of space-time. And if that's the case, then all it does is like make every bit of space expand a little faster. So if it is a cosmological constant, then that ultimately leads to the heat death, which is one of the universe ending scenarios. But yeah, dark energy is just something that makes the universe expand faster than it should, based on our normal understanding of physics, because it it's a weird thing because it makes like it doesn't it acts in a way that nothing else does. So everything else, like gravity, just pulls together, and if when the universe's expansion was set off by the Big Bang, things started moving apart, and then the gravity should be kind of pulling them together, or at least slowing down the expansion.
Mm-hmm.
And dark energy is making the expansion go faster, which nothing else has that property, like that. Nothing else can do that. So it's a weird stuff, whatever it is. But yeah, it makes the universe expand faster, and that's basically all we know about it. Like, it seems to be completely uniformly distributed in space. We have no way of interacting with it. It just does this thing to space-time.
So how are people studying dark energy?
Well, so the main question with dark energy is it a cosmological constant or not?
Right.
And the way that you tell the difference is basically by looking at how the expansion has changed over time, and how, like, basically just trying to trace the full history of the change in the universe's expansion. Because the cosmological constant would do it one way, and some kind of dynamical dark energy, something that changes over time, would do it a different way. So it's mostly that. So people look at tracers of the expansion of the universe, like the supernovae far away that can tell you how far something is and how quickly it's expanding. And then they'd look at things like how galaxies and clusters of galaxies have grown over time, because that's affected by the expansion of the universe too.
Mm-hmm.
And then there are laboratory experiments to try to get at dark energy if it's not just a property of space-time, if it's actually like some kind of new field that's present throughout space, and then maybe we could like manipulate it. So there are experiments to try and do that.
Interesting.
But that's kind of like, there aren't a lot of handles on it. Whereas dark matter, there are lots of ways to study dark matter. Like, we can tell how it collects around galaxies, and we can trace out its influence throughout the universe. And then we can do experiments to try to catch parts of, pieces of it and stuff. So far, we haven't caught any pieces of it. Like, the direct detection experiments have not been successful, but the evidence of dark matter in space has been super solid for a long time.
Yeah, and everybody's been asking, because we talked about it a few times already, about that galaxy that has essentially no dark matter is what they found out recently.
Yeah.
What do you think about that? Because I know people in here are going to be asking me about that all day, and I can be like, we already talked about it.
Yeah, that was really interesting. So I should say, I am not an observer, and I don't work with data, so I can't say for sure, like, if the observation is solid,
Right.
Because I can't comment on that. But as somebody who works on dark matter, it's super interesting, because if it is solid, if this galaxy really doesn't have dark matter in it, then that's fascinating, because for one thing, it means that it has some kind of new formation mechanism, because generally the way you form a galaxy is you have a whole lot of matter and dark matter, like regular matter and dark matter together, and the dark matter kind of helps the regular matter get together, because otherwise the regular matter has too much pressure and it bounces off itself, and it doesn't collapse easily enough to make the galaxy. So normally dark matter should be there. So we'd have to have some kind of different formation mechanism for this thing, and there have been, suggestions for that. But the cool thing about it, if it's real, is that it shows it's like more evidence that dark matter is a real thing, which is kind of counterintuitive, because a galaxy without dark matter showing that dark matter is a real thing seems strange. But the thing is that the main alternatives to dark matter as a real thing are ideas where regular matter just has more gravity than we expect in a weird way. And if that were the case, then every time we saw a whole lot of regular matter, we should also see this like illusion of dark matter from extra gravity from the regular matter. And so if we see a galaxy that has lots of regular matter but doesn't appear to have any dark matter in it, then that really has to mean that dark matter is a separate substance that can be there or not there, right?
Mm-hmm. Yeah.
So it's a super cool result. I I'm interested to see if it holds up, and if it really, like, if there are other galaxies like this, or if this is just a really unusual case. I know that the team that discovered this one is looking at other galaxies and finding, trying to figure out if they have the same kind of situation, or if they also have lots of dark matter. So it should be fun to watch. But I think it's a neat demonstration if it does hold up.
Yeah, someone said maybe not a different formation mechanism, maybe something stripped the dark matter away after formation.
Yeah, so that's difficult because the more likely thing would be if the regular matter was stripped away from the dark matter somehow, because it's hard to pull on dark matter or push on it, because it only interacts with gravity. So, but if you have like a wind from a galaxy or something pushing the regular matter, then you can get that away from the dark matter potentially. And there have been situations where you have collisions of clusters of galaxies where the dark matter passes right through, because the dark matter doesn't really collide with anything. It's this very ghostly stuff, but the regular matter gets stuck in the middle. Mm-hmm. And so you can have a situation like that where the regular matter gets stuck or moved in some way by the motions of stuff being blown out of galaxies, and the dark matter doesn't care. Like dark matter, it's hard to do anything to dark matter. All it does is gravitate. It doesn't collide with anything. It can pass. It's probably passing right through us right now. Mm-hmm.
Yeah, and that's one of those things that I love thinking about too.
Yeah.
Someone asked a while ago though, so what is space expanding to? I get asked that all the time, and I say we don't know, but do you want to?
Yeah. I have this as one of the frequently asked questions on my website, actually, because people do ask this a lot. Yeah. So what is space expanding into? And I don't have an answer that will ever satisfy anyone. It's possible that space is infinite and getting more infinite, which is not satisfying at all. I mean, although we know about the expansion of space is that like things are getting farther apart from each other. So in some sense, things are getting less dense, right? And that's what we can observe. We can observe things getting farther apart from each other. We cannot observe anything outside of our horizon volume, which is this sort of bubble, 46 billion light years on the side. We can't see anything outside of that, even in principle. And out to that edge that we can see, where we can see, nothing looks like it changes in any direction. Like it looks like things just keep going on forever. So we don't have any reason to believe there's an edge, and we also don't have any reason to believe that space like loops around on itself, although it could, but we don't have any evidence for that either. So it could be that space loops around on itself, and that then it could be embedded in some higher space where it could be expanding, but we don't have evidence for that. So it's possible that space has just always been infinite and always will be infinite and just keeps getting bigger. Or it's possible that there's something far beyond our horizon that maybe there's some kind of extra dimensional space. But on my frequently asked questions page on my website, I have a cop-out answer, which is that because it may be that space isn't expanding into anything. It may be that it's just expanding, and so it's kind of like because all we measure is the density change. Mm-hmm. So it's kind of like space is expanding the way that your mind is expanding. Like it's not expanding into anything. You're just getting less dense.
Hey-o, I love it. Oh my gosh, I love that one. Yes, because I think yes, I've read that from you. But I need an FAQ now that I'm thinking about it. I think the question of like what is it expanding into? Mm-hmm. I'm trying to think the other ones. What is dark energy? What is dark matter? A lot of people want to know the Big Bang. Like how can nothing come from something? And then I'm like, well, nothing is something. But mm-hmm. I'm not a QM person really. And I also don't have a degree in QM. I couldn't sit here and really try to formulate works of people that that have been over, 40, 50 years.
I mean, yeah, I mean, this has been a question for ages, right? This was one of Hawking's big things. Like,
Right.
how does something come from nothing? I don't know.
Yeah.
But yeah, I find a frequently asked questions page really helpful, because then I can just link people, to the
Right.
answer.
I think that's something I should do.
Yeah.
Let's see. Someone said, best analogy ever. I agree, Fraser. I heard a mathematical definition. A mathematical definition that treats space like a computer screen. So expansion is not expansion per se, but contraction qua expansion. Kind of like zooming in or out of the computer screen.
I mean, the thing is, like, our sort of experience of space is a lot like zooming in or out, because like our horizon is dependent on how the universe is expanding. And so the amount of the universe we can see is changing over time. And we don't know what's going on beyond our horizon. So you can kind of think about it that way.
Yeah. Someone said, what is her day-to-day life like? They want to know what your day-to-day like.
Right. Yeah. Well, this is my office at North Carolina State University. I come here and I try and figure out stuff. So the day-to-day life, like, I kind of wish that it were more like writing down equations and stuff. I do get to do that sometimes. I have, I don't know, let me see. I've got like some stuff I'm working on, where I'm working on a paper with a colleague, and, there's a whole bunch of equations and we're trying to like calculate some things. And so I get to sit and do calculations sometimes. Oftentimes I do those with the computer. So either I write like Fortran code, or not Fortran. Well, I do sometimes write Fortran code, sadly. Either I write code in like Fortran, Python, C, or like Mathematica or MATLAB, or I just do equations on paper. So I do get to do that sometimes. Sometimes I'm just reading other people's papers and trying to figure out like what the interesting questions are, and how everything fits together. And then a lot of times I'm like teaching. So this year I'm going to be teaching the sort of introduction to astrophysics class. So I'm preparing for that for the fall.
Yeah, and you actually, this is new. Like this happened this year, I believe, because I saw your little plaque. But she just got assistant professor at North
assistant
Carolina.
Professor of physics.
Yeah,
it's very exciting. It's as of January 1st.
Yeah.
So that's why like my bookshelf isn't full yet, because I have all my books are in boxes over there.
Not even moved in yet, guys.
Not even moved in yet. Yeah. I just got my computer monitor this week and it's not working already. So I'm working out the kinks. But yeah, so there's a lot of stuff like teaching and going to meetings and attending talks and giving talks. So yesterday and the day before I was at Penn State University. I was giving a colloquium there and talking to people about my research and about their research and sort of sharing ideas, which is the thing that you do a lot of in academia, is go and talk to other people about ideas and try and find out new things. Earlier today, I was doing an interview for a postdoc position. I'm trying to hire a postdoc, so I was doing a Skype interview with one of the candidates. So that's one of the things that I do as well. I talk to students and stuff. But yeah, I mean, on like good research days, I get some papers together and I do some calculations, and I maybe write some code, and I try and figure out like what the answer to a particular question might be, and what the good questions to ask are. So there's actually a lot of creativity in it, because I get to, like, the area of science I work in is kind of like between the theoretical side and the observational side. Mm-hmm. So like I try and find out what the big questions are on the theory side, and then what the big observations are on the observational side. And I try and find like the interesting ways to connect those, like how you can you can test a theory with a new observation, and what you would see and what the consequences would be. So it's kind of a fun space to be in, and it's a lot more creative and interactive, I think, than most people realize.
Yeah, and that could be so. So how happy were you with LIGO?
Oh, LIGO's amazing.
I know.
Yeah, yeah.
And
Yeah,
then
no,
they,
I'm still just like astonished that we can like we're feeling the vibrations of space-time itself.
yeah. Do you want to talk about that? Because or just how
Yeah.
sensitive so LIGO, guys, in case you don't know, is the Laser Interferometer Gravitational Wave Observatory.
Mhm.
That's a lot of words, so we just say LIGO. Do you want to talk about the sensitivity of that? Because I don't want to botch
Yeah,
that
yeah.
number.
So LIGO is it's a machine that can detect how space-time itself is moving. So Einstein came up with this idea of general relativity, which is the idea that space itself is flexible, and when there's a massive object, space is like curved or bent or like pulled in around that massive object. People usually demonstrate this by like you put a bowling ball in the middle of a trampoline and it makes a dent, and then you roll things by it and they fall in. So that's kind of how space-time works in Einstein's idea of gravity. And one of the other things he predicted related to that is that when a massive object is like moving around, it makes ripples in space-time. And so the way that ripples in space-time look is that they change the shapes of things. So if a gravitational wave like hits you in the face, then what it'll do is it'll make you a little bit taller and skinnier, and then a little bit shorter and wider, and like it'll oscillate you like that. And so the LIGO experiment can detect those changes in the shape of space. So the way it works is they have lasers moving in kind of an L shape, and the lasers are measuring the length of the arms very carefully. And if a gravitational wave comes and shrinks one of the arms and lengthens the other, and vice versa, then it can tell that that's happened. And so it can tell that this wave of disturbed space is moving through. And depending on like the pattern of the disturbance, you can see that like two black holes have collided 1 billion light years away, because of the change in the length of these arms. And the length change that they're talking about is like 1/1000th the width of a proton over 4 kilometers. So it's
Pretty
an
sensitive.
astonishingly precise machine.
And now, but that even developed further. So we've got we've detected a few black hole collisions now, and then we got neutron star collisions, which
that
was
neutron star
gnarly.
collision is super cool.
Yeah, and then now it's just opening up this whole field of science, because I think a lot of people probably thought that would be, this would be like a novel thing. It wouldn't happen all the time, and then they just kind of came in one after another after another.
Yeah, it was funny because for many years, people have been working on this observatory, the LIGO machine, and like when I was an undergrad, they were talking about building it, and like the first sort of discussions of it, they thought they'd have it up by 2000, and it would be detecting things by the year 2000, and then it kind of, and then it wasn't done that yet by then, and then it got built and it didn't hear anything, and for a number of years, like it was just kind of quiet, and we didn't really like anybody outside the collaboration, like we didn't really know what was going on with it. And then eventually they said that like the initial version of LIGO was probably not going to see anything because it wasn't sensitive enough, but maybe they'd get lucky. But then they built this advanced LIGO, and then that was the machine that was like very likely to see something. And so as soon as they turned it on, they saw, like within a couple of weeks or something, they saw this event. It was astonishing, and it was this huge, very significant, very like obvious event. And then and since then they've seen like half a dozen others, including this neutron star collision. It's just been really spectacular.
Yeah, and someone just said, would LIGO be affected by geological movement? I mean, if there are earthquakes.
Yes, yes, totally, and that's why it's such a difficult observation to do, because you have to really make sure there's no other vibration going on, because you're measuring distances, as I said, like a thousandth the width of a proton across 4 kilometers. So those mirrors that the lasers are bouncing off cannot be moving.
Right.
And so there's like this huge like vibration isolation infrastructure, and like it can be messed up by a truck driving by. Like they have to really isolate it completely. And so they have this very complicated system, these very like perfectly built like wires to hang these massive mirrors off of. I mean, one of the biggest sources of noise for this machine is the fact that when a photon hits the mirror, it imparts a little energy and can move that mirror a little bit. So this is called shot noise, the photon shot noise, and like that's part of the noise in the instruments, like the fact that you have lasers bouncing back and forth, and just the pressure from the photons from the lasers can move the mirrors enough to make it hard to see the gravitational waves.
Yeah, and I'm going to change, well, it's not changing the topic, but someone asked a good question. And I know the answer, but I want her to answer because maybe she can expand on it. But do we know of any other black holes near us?
Yeah. So there are tons of black holes that we know about in the Milky Way. There are a lot of black holes that are like stellar mass black holes, where you have a black hole and there's a star orbiting it, and the black hole is like eating that star. And so it turns into this X-ray source. So we see a whole bunch of those. But we also have a supermassive black hole in the center of our galaxy. So that's like 26,000 light years away. And that's called Sagittarius A star. And it's about 4 million times as massive as the sun. It's just sitting there. It's not doing a whole lot. Like every once in a while, it eats a little bit of gas and everybody gets excited because it sort of flickers. But mostly it's pretty dormant, which is good, because if it were eating a lot of, like if it were pulling in a lot of matter, it might get like a jet of radiation and be kind of dangerous. So it's just this sort of dormant black hole. And we know about it because there are stars orbiting very, very close to it, and we can see them like whip around, and we can sometimes see flickering when a little bit of gas does fall in. So it's a kind of neat object.
Yeah, and I mean, we've learned more about this recently, about how many black holes could exist within the Milky Way. I've heard numbers of 100 million. But those are smaller ones. I don't know,
but it's a lot.
Yeah, it's a lot. It's not surprising. Yeah. These are the smaller ones. You know, these are typically faster rotating, these stellar ones, but not all. So I think the closest one is like 1,000 light years away, I think, right?
Yeah, I did calculate this at some point, and I don't remember now, but I'll take your word for it.
Yeah, well, we could just combine and be like, that sounds good.
Yeah.
So let's see, do black holes move? Oh yeah. Everything's in motion. You know, everything's in motion, and even with some of what I showed you, and I saw that you've had this in one of your lectures too, that there's the way that stars go around our supermassive black hole. Dr. Andrea Getz is a person that's done a lot of research on that. And if you back away far enough, you can see the movement of the black hole and how it kind of takes those stars with it a little bit. So it's pretty. Wait, someone said, wait, is this repeatable? I don't even know what they mean. But yes, so everything's in motion.
Yeah.
We move on our Milky Way, and then our Milky Way is moving, and we move as a group of galaxies too.
We're moving toward Andromeda, and Andromeda's moving toward us. And
I love talking about that because people get freaked out, and so maybe this is on your FAQ. What's going to happen to the solar system when Andromeda and the Milky Way collide? Are we going to get ejected?
So I don't have that on my FAQ. We're probably going to be fine. Like our solar system is probably not going to be particularly mess with. But by that time, like the sun is going to have expanded and destroyed all, like it's going to swallow Mercury. It might swallow Venus, and it'll boil off all the oceans and leave the Earth like this sort of charred, like charcoal magma sphere. So we're not going to be too worried about what happens to the solar system by that time, I think. But like a bunch of stars will be ejected. I mean, it's possible that our star will be ejected too, but it's unlikely that our planets will be ripped off of our star.
Right.
It'll just be like all the structure of the galaxies will be totally destroyed, and there will be streams of stars flying everywhere. And like all the gas, when it comes together, will ignite new star formation, and then the black holes might, like when they come together, and they might create new jets, and like they might suddenly become active black holes, and then that's dangerous for anything near those. So it'll be really interesting. It'll be really pretty, probably.
Yeah, there will be a lot of star formation, and that's a good thing because again, that's not happening much anymore.
Mm-hmm.
We like star formation, even if it doesn't involve us.
Yeah, no, it'll be great. It'll be really beautiful from a safe distance.
So it says, so what you are saying is Andromeda is the least of our worries.
Yes.
Yes. That's what I try to tell people too, is that we probably won't be affected as a solar system. We're probably not going to get ejected. Some do, but we're probably okay. But it doesn't really matter anyways, because sun isn't, and it's going to be around its death throes at that point.
Yeah.
And so let's see. Someone said, "Is there a way around this time?" Oh, okay. I don't know if this is like. I should have read your FAQ. Is there a way around this through time travel? Because if not, who knows the amount of civilizations that could have. Okay, so that's not really why I would be interested in time travel. I would like to experience that just to get to nearby systems.
Yeah, time travel would be great.
It would.
Yeah, I think time travel is not too promising. Like there are theorems that say that it can't happen, and we don't but those are not proven. But there doesn't seem to be any way around the sort of how we're stuck in moving through time. Like if we were able to make a wormhole, we could use that for time travel, but we don't seem to be able to make a wormhole. Like it doesn't seem like stable wormholes, traversal wormholes are possible. Like you'd have to have some kind of exotic matter that we don't have access to, and then like even if you had that, it's not so easy to make them possible. But I mean, we can, like we do have like consolation prizes that are similar to time travel, if not actually being time travel. Like we can see the past. In cosmology, we do it all the time. We watch things happen in the past. We can watch the Big Bang itself, so we can see billions of years into the past, which is cool. And we are moving into the future, and we can do that more or less quickly depending on our circumstances, like how quickly we're moving or how close we are to a massive object. So we have sort of the backward time vision and the forward time travel, but yeah, actually moving around ourselves in time is not so easy.
Yes, someone just said, isn't it true that the laws of physics, from what I know, going back in time, there's physics for that, but I don't know if that was just something that I was taught by. I was actually taught that by a professor, but.
Which was the question? Sorry.
So doesn't the laws of physics allow for time travel? But from what I was taught was that it allows only to go back in time.
It's not clear. Like it's not clear how you would do that, like how you move in either direction in time other than just by like existing forward, like moving faster than light, or like taking some kind of shortcut through space sort of opens up time travel in all sorts of ways, but we don't have the capability of doing that, and it might be completely ruled out by physics. So I don't know. I mean, in terms of like, if you built a time machine now that could move you back in time, like maybe that makes more sense than moving you forward in time, but like
Right.
you can just wait and then you're forward in time. So
That you could just
you know,
chill out. Yeah. And that, you know, something that I was asking other guests, but I would love to hear your explanation. And again, like this is something that is something I know people in here might want to ask, but they're not. So why can't we travel faster than the speed of light?
yeah, well, so unfortunately, it seems to be a speed limit, but what happens is that the faster you go, the more energy you need to move that quickly. So, it's kind of like some people say that it's like your mass is increasing as you go faster. You can think of it that way, but really it's about relativity and the energy of your sort of motion. So the energy that it'll take to accelerate you when you're you know when you have a lot of energy from already moving quickly, like it just keeps going up. And so people often talk about it as, you know, your mass is increasing, and as you get close to the speed of light, your mass becomes infinite and you just can't move anything that quickly. But yeah, it's basically like, you know, you can approach the speed of light, but it takes more and more energy to get you moving that quickly. And so the amount of energy it would take to get you to the speed of light is unreachable for any massive object. If you're like, massless objects travel at the speed of light. So like a photon travels at the speed of light. It is light, but like also gravitational waves appear to travel at the speed of light. They're also massless, whatever they are. But they can't travel slower. They can only travel at the speed of light. So you can't, like, there's nothing that can go from less than the speed of light to the speed of light. And that includes like massive objects. You just can't accelerate something that way.
Yeah, yeah, and that's even a better explanation than, you know, because I don't like saying. I just like the way you said that, because when I say that, you know, to accelerate something, you know, it is gradually gaining mass, but also the energy required. That one's difficult. I've heard so many different ways that's explained though, and so it's a weird one.
Yeah.
And we could do one more question and then we can let her get back to being busy. And thank you so much again for taking the time.
No, it's cool. I'm happy to do this. Like I said, I've never been on Twitch before, so it's a neat thing. I should do it more often.
Yeah, no, and I'd love to have you on more often too.
That'd be great. Yeah.
Yeah, because I it's one of those things where this isn't really the platform. You know, I mean, a lot of people will come in here and be like, "This is space on a gaming platform," and I'm like, "Absolutely." So they opened up a section where you could, you know, talk about, well, not talk about, but it's called IRL. And I think space is really IRL. I don't know. I think it's totally in real life. So that I really appreciate it, and hopefully Twitch also sees that, you know, there are people like you, and like we had Phil Plait on, Paul Sutter. We had just a whole lineup of great people, and also Dr. Pamela Gay. She comes on here every Saturday with me, cool. And so yes, so thank you. But I'm thinking of one question that I'm looking at here. Oh no, neutrinos. We're not gonna no. Let's see. I'm trying to see if I can actually find a good one that's short.
Right.
I don't think I can. Wait, can I mix the two? I don't want to, Bill. I want to just talk about space. I don't want to try to learn a video game and talk about space. Oh my gosh, everybody's like, that would be great. Okay, well, I can't see anything. But I think that's good, though. I think that's really, really good. So thank you so much again. And I want you to get back to all of that. And again, congratulations
Thank you.
on the new move. And that's awesome. And guys, we have the link for everything for her. So check her out. And also that book coming in 2020. Yeah, we'll have you back.
Great. Thanks so much. It was really great.
All right. Take care.
Thanks. Bye.
Bye. She's awesome. And now you see a part of my computer.